WDS instruments, which we saw a couple of pictures of those, which are typically called microprobes, if you've heard of that name, are usually expensive. The modern systems are, and they're complex systems. That's why they charge a very high amount of money for the techniques. But their operation generally is complex and is infrequent to be able to find the equipment for a common user to have access to it. So WDS on the SEM, as we saw some earlier pictures in the earlier presentations, is a technique that we want to provide to use to get the capabilities that we need, if it's mapping capabilities or quantification or something along those lines. So we do want to do the WDS. We like it SEM because there are many, many labs with SEM, but we would like to try to get some of the capabilities of the more infrequent dedicated WDS systems. So the newest generation of WDS uses the EDS concurrently to work together. The microprobes typically come from the direction of using WDS, analyzing with WDS, only using WDS and getting the results that way, and they're very highly focused for that, and they're very, very powerful in doing that, but you have to think like an EDS operator, you have to operate like a WDS operator. Everything's focused for WDS. Most of the users in the audience today aren't experienced in WDS as their primary focus. They're an EDS operator, so they would like the WDS to sort of work like an extension of the EDS system. So they want the WDS results, but an EDS mentality, if you will. So the newest, it doesn't always work, but that's the way that they would like it to do. So the modern WDS systems on the EDS use the information both from the factory and during the operation to select and optimize the operating parameters of the WDS to try to get as close to optimum performance out of the WDS as possible. It's always based on how much time and effort you as an operator puts into the system. That's the quality of the results. But the system intrinsically is designed to help out the user. This permits the use of the WDS in a more routine fashion by a larger base of operators to be able to use the system, as opposed to being dedicated operators on a dedicated instrument. Now you can be a little bit more general purpose operator using the general purpose WDS and getting almost the same quality of results as a dedicated operator on a dedicated system. So I'll just talk about what has gone into the team software, as you've seen some presentations on that today, to show what the cooperation is and the handshaking is between the EDS and WDS to give that synergy between the techniques to promote the operation of the analysis of the data in the systems. So as we have seen, the primary benefits that you're looking for usually for here is mostly based on better resolution. Secondarily to that is the very, very low background. So you can see the nice low background here for these overlapping peaks compared to the EDS. Here the background is inclined, so it's not always a horizontal background, but you can see very nice spectral resolution. So it starts with spectral resolution. The second thing is typically low background. So both of those feed into the results that we've seen in the last two presentations. So we want those benefits, so what tasks do we want to do? So you really want to use the WDS for a task the EDS cannot do. So what tasks does EDS have problems with? Well, peak identification confirmation, peak overlaps. That's what you're looking for. And then sometimes trace elements. Then quantification, composition analyses, as we saw in the previous two talks, with overlap peaks usually in trace elements again. Elemental mapping, overlapped EDS peaks and trace elements, and if it has a high EDS peak. So you see where it's coming down to. This is where WDS is primary advantage. Overlapping EDS peaks, trace elemental analysis. That's why you have a WDS. All the manufacturers for WDS systems on an SEM only have one spectrometer. Dedicated WDS microprobes can have upwards of 5 spectrometers simultaneously. So for an EDS operator that just wants help in these fields, one spectrometer can work, but of course, you have to do any multiple elements, as he was talking about 15 elements on the previous speaker. You have to do each element in series. So these are the types of things that you want to do, is overlap peaks and trace elements. So I'll show how the system works for that using the EDS. So as you saw, the new team software has all the WDS and the EDS all built in with the electron imaging. Everything feeds together. So that's the first thing. Dedicated microprobes have WDS software here, tend not to have EDS software. If they do, it tends to be on the side, it tends to be remote. There's no communications between them. So it's just two independent software and hardware systems. The modern systems on the SEM, it's all in one package, makes it real easy, A, for training, and B, that now you have a direct communication path between the two of them. Automatic alignment, as Michaela mentioned this morning, you collect an EDS spectrum, it evaluates the EDS, says iron is the highest peak, automatically sets the WDS spectrometer to iron, automatically communicates with the microscope to adjust the stage height to do it, and you get the nice plot that was shown earlier to see what it is. How does that work? Because of the communication of the system. The system is, in essence, three parts: the electron microscope, the EDS system, the WDS system, communicating back and forth to get the parameters that are necessary to communicate back and forth to optimize the system automatically. The other thing that goes down with just saying, okay, we select iron to go in. So to do that, you actually have to know the iron K alpha peak and not necessarily the average peak, which is for EDS, it can be an average peak depending upon peak overlaps. You want to know what the individual peaks are, so you need to know that. You have to know what the fractor. You have to know what bias to put on the detector. You need to know what the lower electronics discriminator setting is. You need to know an upper electronics discriminator setting. These are all parameters that a dedicated microprobe operator knows, works with, understands, and does every single day. SEM operators tend not to know that. They're not specialists in WDS. They just want to come in, turn it on, have the system run, get WDS quality results out, and get their answers to get through. They're not dedicated operators. None of you are dedicated, very few of you, there's a couple, are dedicated WDS operators. You just want to use the power of WDS to get it done. So all of those other settings are built into the software behind the scenes that you as an operator should realize are there, but hopefully you rarely have to change those parameters. So it goes through and sets it, and that's because of the communication. The auto WDS scan, once again, it goes through, does a peak ID, collects the EDS spectrum, does a peak ID on that, then goes through on each of the elements in the peak ID, does an energy scan across a narrow energy range around that peak. Well, it has to know what the energy of the peak is, it has to know what the lower background energy is, it has to know what the higher background energy is, it needs to know what the bias is, it needs to know what the electronics is. The software does all of that. Why? Because it knows the EDS says it's iron, it's manganese, it's aluminum, it's silicon, it's tantalum. It goes in, goes to the lookup table, knows what the parameters are, sets it up, runs it. You, of course, have the option of changing parameters and optimizing it to get the highest quality results, but it will give you very good results, very little that you have to do because of the communication. Quantitative analysis, once again, set it up. Here you just get the elements, you have to collect standards, either elemental or mineral standards, as we had seen earlier today, to go through. It needs peaks and backgrounds because you always want to deal with net counts. So the background positions. What background positions? They're factory standard background positions. You should qualify them and evaluate those background positions. Most time they're very, very good, but certain alloys there are complications. All of those parameters are built into the system. So that's where it's very nice that the system has all of this built in so that you don't have to think about it. So we will look through some data. We'll go through these pretty quickly because we've seen some data. Trace element detections. This is an EDS spectrum on the background. Don't see very much of a peak to background. What's that? 25% over peak on that, and maybe a 50% peak to background here on the moly and the silicon and the steel. But you can see here's where the background is in WDS, and the peak is way up here. So that's where the automatic peak ID confirmation goes through. It does an energy scan across each of the elements that is questionable in EDS, but is definitely confirmed in the WDS going through. So there's the communication once again. We saw a little bit of question about sulfur and moly overlaps. There's also a lead overlap. And once you do a wave scan, you can see that there's a moly peak here, a moly peak here, and a sulfur peak here. So you can see that in this particular material, there are 3 distinct peaks here, whereas they all overlap in here. Another one similar to what we saw before, silicon and tungsten overlapping. One big EDS and separated on the other peaks. Barium titanate with a multitude of barium titanium overlap peaks. Mercury and sulfur, not a real engineering material, but it does happen. Once again, tantalum, tungsten, silicon, tantalum, tungsten, hafnium, all in the same energy range. EDS really doesn't locate things, but the WDS is real useful for separating them all out. The next 2 slides are a little bit different spin on this. There was some of the lectures earlier were alluding to some of the power of the techniques. This one is trying to emphasize a little bit more. I've purposely done the L lines for brass, for the copper L and the zinc L. As we heard earlier, a lot of analyses are going to lower and lower accelerating voltages in the electron microscope. The advantage of that is to increase the spatial resolution, be able to analyze smaller and smaller features in the material. So many times we'll be going down to 5 kV, 7 kV, even 5 kV, even 3 kV for the beam energy. Once you go down that low, you would like 2 times over voltage of the accelerating beam compared to the characteristic X-ray. So you're restricting the potential X-rays that you can analyze. So in this case, if I put a piece of brass in the microscope and try to analyze brass at, for instance, 5 kV, I don't have the K lines, which are well separated. I don't have the K lines to separate out those. Now we have overlapped L lines that are the only lines accessible. And so to try to do quantification or mapping on the overlapped lines gives us difficulties, but you can see that the WDS can separate out the peaks, and we can get separate peaks so we can do quantification and mapping using the L lines, for instance, for this type of material. The next one is a similar one where I just did a stainless steel. Then if you're running at low voltage, you can't use the K lines, you have the L lines, you have all of the L lines overlapping, so you have chromium and manganese and iron and nickel peaks down here for the L lines, so now you can use that for mapping purposes or quantification purposes. We saw a couple of nice examples of the boron sensitivity. With options, you can go down and detect beryllium. So these are pure beryllium and beryllium oxide, and then here is boron in 2 different moly borides. The other thing to realize is there is a small molybdenum peak with the boron peak, and there is an overlap down there, but you can analyze the boron peaks very nicely. This one, boron in glass. You can see the EDS peak does not really show much, but you can see there's a little bit of a background here, but there is a distinct boron peak. This is the EDS spectrum, and then the WDS spectrum overlapped on it. Quantifications, as we were saying, tantalum, tungsten, in this case rhenium, all overlap, so you can do quantifications there for both EDS and WDS. And as we heard in the previous talk, you use the WDS where it's powerful, you use the EDS where it's powerful, combine the results, and to get a very good result in very fast time. There's another subtle little one that happens every once in a while, that you can have EDS artifacts, pulse polyp, as we were having some discussions over lunch. Sometimes you will have a characteristic line underneath a pulse polyp peak, and the WDS does not have the same pulse polyp problem. So It can pick out the characteristic peak where the EDS would have an overlap and could create some artificial intensity, whereas the WDS would be able to pick out the real intensity. We saw some nice maps earlier. Here's a nice boron map to look through to see where it is. Usually you can get very similar EDS maps out of boron and alloys similar to this, but you have to collect for approximately 10 times longer to get the same quality of the map to do it, to get the signal to noise high enough to see it. So the WDS is really spectacular for low energy X-rays, any of the low energy X-rays, but especially those that are sitting on the high background bremsstrahlen, that it'll separate it out and get much higher contrast. We saw this slide earlier with the EDS peak for the boron. Here's the WDS map for the boron, and much higher contrast. You can see that there's a lot of bremsstrahlen background in the EDS map, and it separates out here in the boron map. This is another one that mostly it's a balance of both peak to background and the peak separation. This is actually from a material which is a machine shop tool. These are tantalum carbides and tungsten carbides. So tantalum tungsten overlap right near silicon. And so with the EDS you have a map that looks like there's tantalum everywhere in the material. But you'll see the WDS map is much higher contrast because the amount of tantalum in the dark regions here is well below 1%. It may be even just a fraction of a percent that's down in there. But the EDS map implies that there's tantalum everywhere, and that's because of the background and the peak overlap. So it's overlapping with the tungsten peak, and there's a finite background in the EDS spectrum. So it's giving us artificial intensity in the wrong locations, giving us a false sense of what the elemental distributions are in the map, whereas the WDS both peak deconvolutes off of the tungsten, and it has a lower background, so it gives us higher contrast in the maps. So this is the proper distribution of the tantalum in this particular material. So let me just see if there were a few other things just based on what I heard earlier. I just want to drop back to make some comments on some other things. The auto Z routine was sort of a question, was someone alluded to. When do you have to change the Z focus on the stage? You have to change the Z focus on the stage whenever you change the sample, or if you move large distances on a sample, in case the sample is slightly tilted when you move across the sample. If you're only moving a half a millimeter or a millimeter, you don't really have to adjust the Z, but if you're moving a far distance, you have to do it. The reason why is all WDS spectrometers are focusing spectrometers. So they focus to a point in space, and you want to get your sample to move to that location in space to bring it up. It just so happens that the EDX spectrometers are axially symmetric, so they actually focus in both the X and Y, if you want to think of that in space to go through. The microspec spectrometer, implied earlier with one of the talks, that it's a lot more flexible in its Z, but it still does have a focus in the Z-axis. There's less of a fall off, but it still is focused in Z. They are all focused in X and Y, that you have to go to magnification of 1,000 to 1,500 because they are spatially focused. With the EDAX systems, the LEX and the TEX, they are, think of them as a parabolic reflector, that they focus to a spot in space that is energy dependent. So at copper K alpha, it's approximately 50 microns in space. You have to put your sample to within 50 microns. That's why we vary the Z in the stage to get to that 50 micron location. But by the same token, it's 50 microns laterally. So that's where all the intensity is. So you need to be a high enough magnification to distribute that. Carbon, of course, is a larger spot, so you can go down to about 200 magnification for that. The other thing, when you have the modern systems for the WDS, if you notice some of the spectra that were up there earlier, you can always tell when it comes from a microprobe compared to when it comes from an SEM. Microprobes are always in wavelength for the spectrum, and I, as an EDS operator, don't understand a wavelength. and they always convert them to EV. But the spectra that are always collected in a EDS system is always collected in electron volts so that you can overlay it onto the EDS spectrum right away. So you can always tell when you see microprobe results compared to SEM results. But it's just a reciprocal relationship to do the two of them. And I talked about that one, and I talked about that one. So that was all my notes from the earlier topics that came up. So WDS provides the results that increase the quality of your quality and confidence of your EDS results. That's the main thing, main reason why you put accessories onto any technique that you have to enhance your results. The modern WDS systems work with the EDS systems forward and back handshaking to give it extra information so that you can optimize it, so you as an operator don't have to remember everything completely about all the techniques. And the WDS have a lot of automation and a lot of automatic settings so that you as an operator can get your work done and not have to remember to set all the settings all the different times. So you should really look for a modern WDS when your EDS performance is lacking, as we said, usually with peak overlaps and with peak to background or trace elemental analyses. So thank you very much. I didn't quite get us back on schedule.